Hi, my name is Michał Włodarczyk, and this is a slightly extended version of my talk for the FOCS conference. This is about my work with Meira Zahavi on planar Disjoint paths, Treewidth, and kernels. Let's get started. So this will be about the Disjoint paths problem, a very, very fundamental routing problem. In the input, here we have an undirected graph G and K vertex pairs, and the task is to connect these vertex pairs with vertex disjoint paths. In planar disjoint paths, we assume that the input graph G is planar, as on the example over there. Here is exemplary solution. And at first glance, you might think that this is just some max flow, but if you try to solve it with max flow, you might end up connecting the wrong endpoints, while we care that red should be connected to red, blue to blue, and so on. So this problem already becomes NP-hard on planar graphs. And the initial interest in planar inputs was due to some application in electric circuit design. And when it is NP-hard, then what can we do? People try to solve it in polynomial time where the number of paths is small, so we get a polynomial algorithm for just two terminal pairs. And for planar graphs, we had polynomial time algorithm for every fixed value of k, so with running time n to O of k. Actually, Shriver gave two algorithms, one based on homotopy, other one based on homology, both highly logical. Then this running time was improved to this one, so the dependence on the input size became linear, and the dependence on the parameter went into the multiplicative constant. From in the modern language, we would say that this was one of the first problems to be classified as fixed parameter tractable, FPT for short, and this gave rise to an entire area called parameterized complexity, where we are interested in running times of this form, some function of the parameter times polynomial in the input size. Next, this FPT running time was extended to general graphs, and in the famous graph miners project by Robertson and Seymour, who developed deep topological theory beyond planar graphs. And this was spectacular project which spanned over 20 papers and had numerous algorithmic applications beside this one. Later on, this polynomial here was slightly improved, but the problem remained that the dependence on k in these running times was really, really bad. These algorithms were even called galactic, possibly because already for small k, the value of f of k might exceed the number of atoms in observable universe. So, you know, these were highly impractical algorithms. The first reasonable parameter dependency was in this one, and yeah, double exponential dependency is reasonable compared to what we got from Graph Miners project, and in a recent breakthrough, we saw 2 to k square times n running time for planar disjoint paths. And this algorithm was a clever combination of the ideas from two former algorithms. And this is the current state of the art. Now let's take a look at what happens inside these algorithms. All the FPT algorithms for disjoint paths are based on some preprocessing, namely Treewidth reduction. Treewidth is a graph width measure, which says to what extent a graph resembles a tree. If Treewidth is small, then we can employ some dynamic programming techniques to solve problems alike on trees. So reducing Treewidth to be some function of k helps us design FPT algorithms. And for general graphs, we knew that it is possible to reduce Treewidth to some implicit function of k. And in planar graphs, the situation is better. There is a way to reduce Treewidth to be single exponential in k. And people wondered whether you could do better here, because that would immediately yield an improvement in the running time. Ideally, we would like to reduce Treewidth to be polynomial in k, but so far we lack techniques to address this question. Then there is a stronger notion of preprocessing called kernelization, where we not only want to reduce width of the graph, but size of the graph. More formally, kernelization is a polynomial time procedure which takes an instance and produces equivalent instance of size f of k. And kernelization is nice because there is a framework for showing hardness in this paradigm, and already in 2009, the polynomial kernelization for general disjoint paths was ruled out, which is hardly a surprise because we don't even know how to reduce Treewidth to any like reasonable bound in k, let alone the size of the graph. But the interesting question was here whether we could get a polynomial kernel for planar disjoint paths. And here we didn't really know what to expect, because from one hand, we knew that the current techniques cannot get Treewidth below 2k. But on the other hand, we know that planarity facilitates kernelization very much. We have really hard problems like k-dominating sets, which are even not FPT on general graphs, but they have even linear kernels on planar graphs. So our first result is a resolution of this question mark. We show that planar disjoint paths doesn't admit a polynomial kernel under the standard complexity assumption. And for those of you working with kernelization, it might be of interest that we also rule out a weaker notion of polynomial two-ring kernel. And this hardness also carries over to the variant of the planar edge disjoint paths, where we didn't even had hardness on general graphs. Recall that on default, we speak about the vertex disjoint paths here. But this is not the end of the story. Our second result says that planar disjoint paths does admit a kernel, but for the parameter k plus Treewidth of the input graph. And this has a few interesting consequences. First of all, we know that Treewidth can be reduced to single exponential, and then when we plug it in here, we get a single exponential kernel for the problem. Next, we can pipeline this with the known n to O of k algorithm and obtain 2 to O of k squared parameter dependence matching the state of the art in a simpler way that it was done before. And the last consequence is maybe most surprising, because we know that we cannot compress the input to be of size poly k, but we could do this when the Treewidth is small. So as a direct consequence of that, we get that it is not possible to reduce Treewidth to be polynomial. And And yeah, so right now the preprocessing complexity for planar disjoint paths is fully deciphered. Now I will speak a bit about how to get this hardness of kernelization. We reduce from the classic set cover problem, where we have a universe U of size k and the set family over this universe. These sets are drawn with colors here, and integer L. And we ask whether we can pick L sets from this family to cover the entire universe. And we parameterized set cover with the universe size k. Set cover is known to be hard for standard kernelization and for Turing kernelization. And to transfer this hardness into planar disjoint paths, we need just a proper reduction. And this reduction is so-called polynomial parameter transformation. That is a polynomial time reduction from set cover with parameter k to planar disjoint paths with parameter poly k. So if we had a polynomial kernel for the second problem, that would imply a polynomial kernel for the first one. And now there is an important observation about the problem, which guided our construction, namely that planar disjoint paths can be solved in polynomial time once we fix the homotopy class of a solution. Two solutions are homotopic if you can transform one into another by pulling or pushing these curves while keeping them disjoint. For example, these two solutions are not homotopic because these two paths pass each other like in different ways. This observation was made by Schreiber, who also showed that there is roughly there are N2K homotopy classes, and this led to N2 of K time algorithm. For us, it is important that the homotopy class forms an NP witness for the problem. If you try to convince me that some instance is solvable, you could just provide me with an encoding of this homotopy class, and I could verify if there is a solution in polynomial time. It is expected that polynomial time reduction should not reveal too much information about the NP witnesses. So this reduction should map different NP witnesses for set cover, so tuples of sets into different homotopy classes. Yeah, so that is some intuition. To be more precise, consider an instance of set cover with universe of size k, set family F, and target L. And now for element E from the universe, we would like to encode the family of sets containing this element. And the challenge is that this family might be as large as 2 to k, but in order to have a meaningful reduction, we can only use poly k paths. So we cannot afford creating even a single path for each set here. So to do it in a different way, we index the family F with binary strings of length k, and then the family Fe corresponds to a subfamily of such binary vectors. Now there is a nice way to represent a binary vector with homotopy. So consider the toy instance and the path between these two black vertices. This path needs to make a choice for each colorful vertex, whether to pass it from the top or from the bottom, and this can be encoded with a single bit. And in this example, we have a path corresponding to vector 1, 0, 0, 1, and this is an example for vector 0, 1, 0, 1. The choice of this homotopy class enforces directions for the remaining paths here. So these colorful paths needs to either take lower passage or upper passage, depending on this vector. Now we can draw such a curve on the plane with this property that every colorful path must cross it at some point. And since these paths are disjoint, they need to cross this curve at a different place. So in some sense, the length of this curve indicates how many crossings we can have here, and this length of this path is where we would encode the information about which vectors are good or bad. In order to encode this information, we take a dual perspective. So we look at the dual graph of this part of gadget. In a dual graph, every face becomes a vertex, and the edge between two faces becomes an edge connecting the corresponding new vertices. And the old vertices becomes faces now. We are interested in a setting with two distinguished vertices S and T on the outer face, and in the dual we create two vertices for the outer face, one on the left and one to the right. This picture is more about edge disjoint paths, but this doesn't really matter here. It just makes the pictures a bit clearer. So now there is a nice property that when we have an ST path in the primal graph and S hat, T hat path in the dual, then these paths must cross at some point. And when we have a family of edge disjoint paths in the dual, then each of them needs to cross this ST path in a different place. So the length of this path imposes an upper bound on the maximal flow in the dual. From the left to right, and we are interested in the shortest such path because then we get tightest upper bound. So this is how the dual of this part will look like. These four distinguished faces correspond to these four terminal vertices. And now this curve corresponds to an ST path in the dual of the prescribed homotopy. Now every path in the solution that obeys this homotopy needs to cross this orange path, and also every path of the primal going from the top to the bottom also needs to cross it. So once this vector 0, 1, 1, 0 is chosen, then the length of such a shortest path imposes an upper bound on how many paths we can route here. There are examples of shortest ST paths for homotopy given by 0, 1, 1, 0, and the green one is for 0, 0, 0, 1. In general, this graph is chosen is constructed in such a way that for each homotopy class, the shortest ST path should go as straight as possible. And the crucial property that really is the crux of the reduction is that for each homotopy class we have a unique shortest ST path. So if this ST path is unique and its length imposes an upper bound on our flow, then to accommodate one more unit of flow, we just need to extend increase the length of the shortest path by 1. Another nice property is that these paths are edge disjoint, And to increase length of such path, we can just subdivide the first edge on this path. So now we have 2k different homotopy class, and for each of them we can encode a bit of information by subdividing a proper edge. And this addresses a main challenge here, that we can have a gadget which stores 2k bits of information while using only k paths. In proper construction, there are other like building blocks and stuff gets slightly more complicated. So in the paper, we have pictures like that. If you like figures that resemble some electrical circuits, then I encourage you to check out the paper. We have a lot of such figures. And last remark about this construction is that in this gadget, we create grids of large size. When we have large grids, then we have large Treewidth. And this is unavoidable in the light of our second result, about which I will talk right now. So the second result is a polynomial kernel for the parameter k plus Treewidth. And the idea of this kernelization algorithm is to reduce the problem to the case where all the terminals lie on the outer face. It is pretty common for planar problems to become way simpler for this case. How we can do this? We can draw a tree on the plane that connects the terminals, and if we need to cross some other vertices in this drawing, we mark them blue, and then we can take scissors and cut the plane open alongside this tree and widen this fissure. So now some vertices might get split. For example, this one gets split into 2 copies. This one gets split into 3 copies. And now all the terminals are incident to a single face. We can now flip the embedding to make it the outer face. Now there is easy correspondence between paths here and paths there. When a path crosses our tree, then it also gets split into a collection of paths. And when we can preserve the structure of disjoint paths while compressing this graph, then we can also preserve the structure over there. And this case is easier, for example, because there is not much topology left in here. You can see that there is only one homotopy class of a possible solution here. But there is a catch. In order to preserve this structure of disjoint paths, we must treat these blue vertices as additional terminals. So we need to guarantee that their number is small, that it is polynomial in the parameter. So what can go wrong? The worst case scenario looks as follows, that we have some terminals here in the inside, now a deep well of concentric cycles in the graph, and some terminals in the outside. So if we try to construct such a tree on the plane, then we would need to cross every cycle here, and we would have a lot of blue vertices. So we somehow need to get rid of this bad scenario, and here Treewidth comes into the play. So if we have a lot of concentric cycles, then if we had a large number of disjoint paths going from the interior to the exterior, then we would have a large grid minor. If we had large grid minor, we would have large Treewidth. So conversely, if Treewidth is small, then the flow is small, and so we have small separators between interior and exterior, and we take advantage of this fact in several ways. This fact was also exploited in previous parameterized algorithms for planar disjoint paths, but we use it in a different way. Namely, we show that whenever you have such a picture, then you can always find an edge which is irrelevant, meaning that as long as there is some solution, then you can also find a solution that doesn't use this particular edge, so you can safely remove it from the graph and get an equivalent instance. Now the algorithm is as follows. We take an arbitrary planar bending of the graph and look at the radial diameter of this planar bending. So the maximum number of faces you need to cross to get from one vertex to some other. So maximal radial distance. And when this radial diameter is this big, then you can always find a structure like that, and you can identify an irrelevant edge and remove it. And you can repeat this process, shrinking the graph at each step, and at some moment this process terminates, meaning that the radial diameter is small, and now you can reduce to a single phase case by the argument from the previous slide. That's the outline of the algorithm. Now I will conclude with a few open problems. So the state of the art for planar disjoint paths is parameter dependence 2k squared, and the only lower bound under exponential time hypothesis that we have is of this form, 2 square root of k. And this follows directly from the NP hardness proof of the problem. So there is a pretty big gap between these bounds, and tightening this gap in any direction would be very interesting. Secondly, there is an ongoing research project called efficient graph minors, where people try to make these arguments from graph minors theory algorithmically efficient, so to get rid of these galactic running times. And after understanding the complexity of disjoint paths on planar graphs, the next natural step is to understand it on graph classes excluding a minor. And we would like to have this kind of efficient running times also there. Next thing is is the complexity of the problem on directed planar graphs. We know that for this setting, the problem is also FPT, and the running time is this double exponential in k. And we would also like to improve it to single exponential, to have a nice running time like that, or maybe it might be the case that this is unavoidable, and maybe double exponential dependence is necessary. And the last question is more open-ended. So we showed by a combination of two results that planar disjoint paths does not admit a polynomial Treewidth reduction. And the question is, can you observe similar phenomenon for other problems? Or maybe can you rule out polynomial reduction of some other relevant parameter, like say dimension or something else? That's it. Thank you for your attention. Bye.